Let's take a look at read-only memory, or ROM. So a ROM is a memory device that's information is permanently stored once it's specified by the designer. It's non-volatile, so the information is going to stay there even if the power is turned off. If we look at a block diagram of our ROM, we have K inputs and N outputs. The inputs are address lines. They select which address space will be presented at the output. So we can think of it in terms of a register. It's specifying which of these registers, we have n-bit registers, is going to be available at the output of the device. It probably is also going to have one or more enable inputs not shown here, so that the ROM could be, we could use multiple ROMs in sequence. So this is our block diagram for a 2K by N ROM. So the K addresses can specify uniquely 2 to the K different address space, and those address are the inputs to the ROM. The output stored is the memory at that word stored in ROM. So, but there's no data inputs. So how do we get the data into the ROM? That data is stored into the ROM prior to it being used in the system by the designer, by hardware. So again, if we look internally at this 2K by N ROM, we're specifying I for the inputs. So I 0 to K minus 1 are the inputs to this decoder. So those K inputs to the decoder can uniquely specify 2 to the K different outputs. So if the input is selecting one of the addresses, the output of the decoder will be a 1. So if it's the inputs are specifying address space 2, the output of decoder at 2 will be a 1 or 5 volts, and the output at all the other outputs will be a 0 or 0 volts. And then we have at our outputs here, we're using A for the outputs as though it's the output of a flip-flop. So the 0 to n minus 1 outputs, each of those are being driven by this OR gate, this fishtail OR gate that's connected to each of these points in here, and we have K of them. So each of these points is where we're considering the data to be stored. So if you recall, the way we look at these cross-point switches, initially all the fuses in it are intact. If the fuse is blown, then weirdly, if the fuse is intact, the X is there. If the fuse is blown, there's no X. So this, if we look here at the output of A n minus 1 here, the most significant one, up here, this fuse is intact, this fuse is blown, this fuse is intact, blown, intact, blown. So that's internally to our ROM. So we have our 2 to the K by N ROM has an internal K by 2 to the K times 2 to the K decoder. It has N of these OR gates at the outputs. It can address, it has 2 to the K words of each N bits stored in it. And then what's in here in this cross-point switch, this is our programmable interconnections. So this is how it's stored by hardware prior to being used. So this is the thing that we want to look at a little bit further, is this cross-point switch. So let's look at an example of a 32 by 8 ROM. So we have 32 words of 8 bits each. It needs 5 addresses because 2 to the 5 gives us the unique 32 identifiers, and each word has 8 bits. So we need 8 data output lines, so it like stores a byte. Each word is a byte. And so internally here we have our K is equal to 5, so we have a 5 times 32 decoder. And again, so now we can see all of this cross-point switch here. So that's our 32K by 8 ROM. The address inputs into the decoder, the data outputs at the output of these OR gates. This cross-point switch is what we want to look at further. So the two conditions of this cross-point switch: closed means the two lines are connected, open means the two lines are disconnected. So this shows right here, it shows no X's here, so it shows as though all the inputs are disconnected. But each of these points here, each of these intersections, the point can be open or the point can be closed. It's normally closed, so the 2 points are connected. It's opened or blown by applying a high voltage pulse. So what does that mean? Then how do we get the zeros or the ones? If we look here at the output of the decoder, for example, if we're selecting address space 3 here, so our inputs are I4 to 0 are selecting address space 3, the output of this decoder, that AND gate, remember there's all these AND gates, that'll have 5 volts, and the output of all the other decoder outputs will have 0 volts. So if and then what is in this cross point switch, we have the fuse and a resistor to ground, and then we have the connection to the AND gate. So this is what at the other side of the fuse is what's connected to our OR gate, our fishtail OR gate. So if this fuse is not blown, then we're going to be connected to 5 volts. And we get a 1. If the fuse is blown, we're going to be connected to 0 volts and we get a 0. If we look at output of 2, since it's not selected, there's 0 volts at the output of the AND gate. So whether this fuse is blown or not, we're going to end up at 0 volts for the input to the OR gate. So only one of the inputs to the OR gate can possibly have a logic 1 or 5 volts. And so if what's stored at that input is a 0, then this fuse is blown and we get 0 volts. So that's how we blow the fuse or not. So again, if we zoom in and take a closer look, if we look at here at address space 3, since this has an X in it, that means that fuse is intact. So that fuse is intact, so this is a short circuit. So this is a short circuit, so we're going to be connected to 5 volts when address space 3 is selected. The next fuse is open. So it's going to be, since that's open, it'll be connected to 0 volts even though address space 3 is selected. At address space 2, we have both of these fuses are intact, but we have 0 volts connected on both sides of the fuse, so we end up with a 0 as the input to the OR gate. So if we look here at data at address space 3, what we have is a 1 0 1 1 0 0 1 0. So the input to OR gate A7 here is going to be, we're going to have a 1 here, and even though we're storing a 1 at address space 0 and at address space 2, the output to the AND gate is a 0. So we don't get to see what's stored there. We don't get to find out whether that fuse is blown or not. So that's how the cross point switch works internally, and it's important to remember X means the fuse is intact in order to read this diagram properly. So this asks, what is stored at address 29? Well, we have stored at address 29. We have, if we're going from A7 to A0, we have a 1 1 1 0 0 0 1 0. And it's not unusual to think X means the fuse is blown, because that kind of makes sense to me. So you need to understand that X means the fuse is intact to be able to read this. If you read it incorrectly, that's a systematic error that can be corrected. But if you think about this, what we have here is just a truth table of data of 1s and 0s, and that truth table tells the ROM programmer whether to blow the fuse or not. So again, if we so that's what's stored at address 29, and then we can convert that to base 10 to 26 base 10. All right, so we can represent ROM information in a truth table, and that's kind of key, and we'll look further at that in the next video.